Okay, so this is the last section for Math 112, rational functions. There's actually 3 lectures here, but they're all connected together. So a rational function is a quotient of two polynomials. So 2x plus 1 over x squared minus x minus 6. And when we want to graph this, we want to know 3 things. We want to know end behavior, what happens at x values where the denominator is 0, and what are the x-intercepts, right? And if you go back to think about polynomials, end behavior and x-intercepts, we talked about that. But polynomials were defined for all real numbers, and these ones aren't. And so we have to be careful about dividing by 0. So we'll deal with the end behavior of rational functions. We'll first look at this function, 1 over x, and then this, and then 3 other examples. And then we're going to end up graphing the 3 other examples. So end behavior means when x is very large and positive, what does the graph look like? Or when you go way out to the right on the graph, what does the graph do? And if x is very large and negative, that's end behavior to the left. What does the graph look like? When the graph goes way out to the left, what does it do? There's some specific notation for this, and I mean, mathematicians have notation for everything. If f of x is a function, limit as x go to infinity, limit of f of x as x goes to positive infinity. This is what's going out to the right. Limit as x goes to minus infinity. This tells you about what happens to the left. I don't use the notation much, but it does end up in some of my math lab problems, so be careful about it. So what's the end behavior of 1 over x? And I don't know why I gave myself so little room there for x, but suppose we take a really big x, like 1,000,000. Suppose x is 1,000,000. What's 1 over x? Well, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 5 zeros and a 1 at the end. It's a really small number. If you make x 10 times as big, right, 1 over x will have 1 more 0. 1, 2, 3, 4, 5, 6. It's gotten 10 times as small. If you make x even bigger, right, 100 million, 1 over 100 million is, how many zeros do I have here anyway? 1, 2, 3, 8. 1, 2, 3, 4, 5, 6, 7, 8, and a 1. So very, very small. So as x gets bigger, 1 over x gets smaller. What about for negative x's? Well, if I look at minus 1,000,000, the only difference is that I'm just going to have a minus sign. So minus 0.000001. And if I had minus 10 million, I'd have minus 0.00000001, right? So what kind of points do we have on our graph? If we're way out at 1,000,000, your y value is really small, right? If this is 0.000001, then 1 is going to be, on that scale, it's going to be like way off the top of the graph, right? Because that's a very small number. And if you're at minus 1,000,000, minus 1, comma 000, comma 000. So if you're out at minus 1, it will be a very small negative number. And the further you go out, the closer you get to the x-axis. So the end behavior for y equals 1 over x is basically the x-axis. The graph drops down to the x-axis. So when we think about 1 over x, we graph it like that. And that's the end behavior. Something else happens in between, so that's what the end behavior looks like. So any end behavior function that's 1 over x raised to a power, like 1 over x, 1 over x squared, 1 over x cubed, 1 over x to the 4th, etc., they all have the horizontal asymptote y equals 0. The x-axis is the end behavior. As x gets bigger and bigger and bigger, y approaches 0. So limit as x goes to infinity of 1 over x to the n equals 0. Limit as x goes to minus infinity of 1 over x to the n equals 0. Okay, so how can that help us with the function, this function? So y equals 2x plus 1 over x squared minus x minus 6. I want to know about the end behavior. So what I'm going to do is a little bit of a trick. I'm going to factor out a 2x out of the top. And an x squared out of the bottom. So when I factor something out of the top, that means I just rewrite it as a denominator for everything else. The 2x comes out, 2x times 1 is 2x. 2x times 1 over 2x, that's my 1. X squared times 1, that's my x squared. X squared times x over x squared, the x squareds cancel out, and I'm left with minus x. And then if I distribute this x squared to this, I get minus 6. So I get this, right? And I'm not worried about the denominator being 0 because I'm actually interested in the end behavior if x is really, really big. So if x is really big, this is basically 0. This is basically 0. That's basically 0. So this fraction then becomes 2x over x squared times 1 over 1, which if we simplify it becomes 2 over x. So for very large x, my graph of this complicated function, right, really looks a lot just like the graph of 2 over x. And we know what that looks like. I have x's in the bottom, so my end behavior is just the x-axis. So that's not too bad. So we can generalize this. What actually happens here is that we're looking at the fraction of the highest terms in the top and the bottom to determine the end behavior, right? Because the other terms really don't matter. So to find the end behavior, find the leading terms in the top and the bottom, form the ratio, cancel out as many x's as you can, and see what you get. So for this one, what's the leading term in the top? You've got a 3, an x squared, and then an x. So that's a 3x cubed. I've got 3 factors in the top, so this is going to give me x cubed multiplied by 3. Leading term in bottom is an x squared times an x, which is an x cubed, right? We've got 3 factors in the bottom, so that means if I multiply that out, I'll end up with an x cubed. So end behavior, y equals 3x cubed over x cubed equals 3. So my end behavior is y equals 3. How do I graph that? Well, here's 3. I want just the end behavior. So the line y equals 3 is this line, but I just want the ends of it going out this way and going out that way because that's what the end behavior is. The graph will do something weird in between. We're not worried about that. When we get out to the sides, it's just going to be y equals 3. So that's the end behavior. What about this one? What's the end behavior? Well, I'm going to find the leading term in the top. So there'll be a minus 2, and I've got 1, 2, 3 factors in the top, so minus 2 over x cubed. And then, not sure that should be, well, we're going to make this just an x plus 1, x minus 1, so I can have a separate thing. So this becomes 2x minus cubed, then x squared. So this becomes minus 2x. So I've got 3 factors in the top, 2 factors in the bottom. So I have an x squared in the bottom, a minus 2x cubed in the top. Cancel out as many x's as you can, you get a minus 2x. What does minus 2x look like? Well, it's a line, right? It's a parabola. It's not a parabola, it's a line. It's a type of a polynomial. And we know what that is. It's an odd power with a negative coefficient. So its end behavior just looks like this. Oh, there we go. So odd power means up on one side, down on the other, but a negative coefficient means we'll be going up to the left and down to the right. Okay. And what about this case? What's my end behavior going to be? I've got 2 factors in the top, so that gives me x squared. In the bottom, I've got 5 factors, so an x to the 5th in the bottom. So that's 1 over x cubed. We know that whenever you have x's in the bottom, that means that y equals 0 is the end behavior, is a horizontal asymptote. Behavior, I hope that's spelled correctly. So your end behavior is like that. So there we go. So there's 3 types of end behavior for rational functions. If you've got more x's in the top and the bottom, it's like a polynomial. So in this case, x cubed over x squared. If you have the same power on the top and the bottom, end behavior is a horizontal asymptote, but not the x-axis. And that was this, where we got the y equals 3, right? X cubed over x cubed. And then finally, if you have a lower power on the top and the bottom, you get the x-axis, right? X squared over x to the 5th. That's a 1 over x cubed. So you get something like that.